All right, so this next chapter that we move into is entitled Internal Flow. Internal flow, so that's flow in a pipe or flow in a duct. Doesn't have to be a perfectly round pipe, but it's some structure that contains the flow and directs the flow, channels the flow. And also when you have pipes and ducts, you'll have fittings that take and split the flow, join the flow, control the flow, make the connections so it goes in a larger cross-sectional area pipe or smaller, and so those things we'll also take a look at. There's a lot of topics to cover. Just kind of point out a few of the main themes. We'll revisit the Reynolds number. We'll talk about laminar flow and turbulent flow in pipes, internal flow. Talk about the entrance region. Talk about diagrams and equations in order to be able to predict the head loss, which is the pressure drop or the head loss in straight run sections, as well as the head loss in fittings where you have significant pressure drops or head losses. Then we can put things together into a network. We talk about the system curve, which is a good lead-in to turbo machinery because you match a pump to the system. You size a pump to drive the flow that you want in the piping system that you've designed. So hopefully this is a fun chapter, very applied chapter, very useful chapter for you. So let's talk about internal flow inside of a pipe. Let's talk about this pipe right here. We typically try and draw it like that with the center line running down the middle of the pipe. We'll talk about R, the coordinate system, going from the center line where R is equal to 0 out to cap R, which is the radius of the pipe. So a lot of times we work with the coordinate system where R goes between 0 and cap R. And if you turn the pipe and look at it going down the pipe, here's the center line. Maybe you're interested in a little section that, I'm not drawing it too well, goes from R, lowercase r, to lowercase r plus delta r. And so that's that cross-sectional area that would be if you went looking down the pipe. Often our velocity profiles, almost always, I can't think of any case that's not, where it's not just one-dimensional, and we would sketch it by the velocity profile looking like this, where you talk about u, that's the speed u as a function of r. Well, u is down in this other direction. Maybe you call it the x direction. Maybe you call it the z direction. Often we call it the x direction, down the axis of the pipe. So u is the velocity in the x, so maybe u sub x if you wanted to emphasize that, or just u is a function of r. If you take a look at this profile right here, what can you tell about two things I'm interested in? Is anywhere the velocity equal to 0, the fluid speed equal to 0? Yeah, at the wall. And what type of boundary condition, what term did they use in fluid mechanics chapter 1, I think it was, to say no slip, no slip. So at no slip at the wall, hence u at cap r is equal to 0. And where's the maximum? So the maximum is at the center line. Think about this. If I move a little bit away from the center line, what happens to the speed? Does it go up or down? If I move a little bit away from the center line, maybe it goes down a little bit. How about if I think about going this way? I know that our coordinate system does not run from negative r to positive r, but I know it's symmetric and everything, but think about if I move a little bit this way, going either above the center line or below the center line or to the right of the center line, to the left of the center line, the speed goes down. And so what mathematically can you say for a boundary condition applies to u at the center line? It's not that we know the magnitude, but we know the slope. So you have that du dr. What is that? That's the slope of the velocity profile evaluated at R equal to 0, meaning evaluated at the center line, what does that have to equal? 0. Yeah. It's as if the slope is flat right there at the center line. So those are two boundary conditions that we'll use again and again today, or at least once or twice today. Then we talk about the average velocity, maybe UAVG. Well, we know that it's high at the center and low at the edges of the wall. So what is a mathematical equation? Somebody says, give me the mathematical equation to calculate the average velocity for flow in a pipe. What would it be? I'm going to pause, walk around, and see what you write down on your sheet of paper. So when we think of averaging, we think of taking a sum of things and dividing by something else. So if I said, here's 6 numbers, I don't know, 2, 3, 4, 2, 3, 9. How many numbers is that? 6 numbers. Can you give me the average of those 6 numbers? Sure. What would you do? You would sum up each of the numbers and divide by the number of numbers. Would you not? So you'd take 2 plus 3 plus 4 plus 2 plus 3 plus 9, and then you divide by 6. Wouldn't that give you the average of those 6 numbers? Well, it's the same thing in mathematics when you have a distributed, not discrete function. Like instead of 6 individual numbers that are discrete, you have a continuous distribution. And so what's the equivalent to this symbol for summation? Integration. Right, and so we're going to have the integral of what? And then we're going to divide by something. Well, it's the integral of the u as a function of r dA. So it's the sum of the speed over all of the area, the cross-sectional area of the flow. And then you divide by the area. That's it. It's very similar to this equation for getting the average of a group of numbers. So it's the integral of u. You don't even have to put function of r. It's just the integral of u times dA, integrated over the area, divide by the area. That gives you the average speed in the pipe. Some people wrote, well, this is going to be 1/2 of u max. Well, either you've read ahead, which is good, or you just know that that's for laminar flow, and we're going to derive that. We're going to reestablish that result. I encourage you to take a look and solve a lot of problems. Today I'm going to show you problems, but I'm not going to take the time to solve them, unfortunately, because I want to go a little faster. But things like water flows steadily in an 8 millimeter diameter pipe at a flow rate. What is this? This is a volumetric flow rate, sometimes Q, used for that symbol. And the flow is laminar. The velocity in the center of the pipe is, well, here the velocity in the center of the pipe, U at the center of the pipe is the maximum. You're going to use the result that the maximum is twice the average. Okay? And to calculate the average, you have that A, U average. I know we switch between U and V sometimes, but it's the velocity, the average velocity, is equal to the volumetric flow rate. And so U average for this problem is the volumetric flow rate 1.15 liters per minute divided by the cross-sectional area for a 8 millimeter diameter pipe, pi d squared over 4. You get the right units, make it work. Get the average velocity multiplied by 2, get the maximum velocity, and that's the velocity of the center of the pipe, assuming it's fully developed and laminar flow. What's the velocity halfway between the wall and the center of the pipe? Well, you have to know what the velocity profile looks like. For laminar flow, u as a function of r is equal to u max 1 minus r over cap r squared. Where'd that come from? Well, we're going to rederive it in a little bit, but it's our analytic equation for the velocity profile. This is a function of r. Can you see that? It's a function of r. What does it look like? It looks like a quadratic. It's like if I plotted a minus cx squared as a function of x. It would go something like this, wouldn't it? It's quadratic. And the velocity profile, here's the center line, function of r is quadratic. That's what we're plotting, u as a function of r. Okay, so anyway, if you said that you want it halfway between, well, you calculated the maximum, that's good. Put in lowercase r equal to 1/2 cap r. If you put in 1/2 cap r, then I'm running out of room, but this becomes u max times 1 minus 1/2 squared, which is 1/4. So it's 3/4 of u max. Okay? All right, let's press forward. So we already covered volumetric flow rate, Q, often AV. This is at the average speed going down the length of the pipe. And then what's the mass flow rate, m dot? I don't know why. Sometimes we put dots on some things, sometimes we don't. You just have to know, okay, Q could be for volume, and Q dot for volumetric flow rate, but it's never written that way. It's just always Q for volumetric flow rate. And M dot for mass flow rate, but it's just rho times Q. What happens if the velocity profile is given by this equation? We'll take a look at it. It's not quadratic, is it? U as a function of r is equal to u max times 1 minus lowercase r over cap r, all of that to the 1/6 power. That's not a quadratic equation. If you plotted it, what would it look like? Let's compare it to a quadratic. What would it look like? It'd be a little flatter in the middle and then come down a little steeper at the edges. That's what this profile will give you. Somebody says determine the average velocity in the pipe for that profile. Well, you would go back to u average is equal to 1 over the area integral of u as a function of r dA. To make this integration, you would use the integrate over the whole area, you would use 2 pi r dr. And that's basically that ring. You would sum up over rings as you go out further and further from the center line. And then you would stick in u max, and then 1 minus lowercase r over cap r, all of that to the 1/6 power, integrate, and then the area of the pipe hasn't changed, it's pi cap r squared. You integrate from 0 to cap r. So there's the equation for u average. And what you find is it'll boil down to something times u max. And when it was the laminar profile, it was 1/2 of u max. And when it's something like this, which is turbulent, it's not 1/2, but it's closer to maybe 0.7, 0.8, 0.9 u max, somewhere in there. It's not 1/2 u max, it's something larger. Well, for this problem, you can cancel the pi. You can take this cap r squared, put it underneath here, and put it underneath here. You introduce a new integration, take this outside, the integral, and you would integrate from 0 to 1 of 1 minus x to the 1/6 x dx, where what is x? A new variable, which is lowercase r over cap r. And so now I make it into a simple integration. Here's u max. And I don't like to do these integrals as much as you do, so I go and do them in Wolfram. And I left out the 2 right here. So we'll put that in. So it's 2, 1 minus x to the 1/6 power times x. Integrate from 0 to 1, and it comes up almost 0.8, 0.79. So in this case, for that velocity profile, U average is equal to 0.7912 U max. 80% of U max. We already talked about laminar flow and turbulent flow. Who did a lot of experiments that characterized the difference between laminar flow in pipe and turbulent flow in pipe? Osborne, Reynolds, those are the years that he lived. How did he do it? He basically had flow. He had a very slender little tube to come in and introduce some dye. And he watched the dye. In certain cases, the dye got all jumbled up in the flow, well mixed within a short distance after introducing it. It was turbulent. Some flow cases, the dye stayed in that layer of the fluid and didn't get well mixed up. Difference between laminar and turbulent. So we in fluid mechanics characterized the Reynolds number for flow in a pipe of diameter d, and that's equal to, can you write the Reynolds number from memory? Rho, U average, or V they call it, d divided by mu. How can you interpret the Reynolds number? The ratio of 2 competing forces, inertial in the numerator and viscous in the denominator. And so when the inertial forces are large compared to the viscous, that means the Reynolds number is high, and that's going to be an indication that you probably have turbulent flow. When the Reynolds number is low, the viscous forces dominate, hence you expect to have laminar flow. What is the critical Reynolds number for flow in a pipe that would distinguish between the two? Say, oh, if you're above this number, turbulent. If you're below this number, laminar. Around 2300. Some people would put 2100. Some people just round it off to 2000. But probably more than half would say 2300. Where did that number come from? Any theoretical analysis? No, just a lot of experimental observation. Lots of experimental observation. What happens if you have flow in a non-circular pipe or duct? Well, you have these often. You have airflow in a rectangular duct. Well, what you do is you try and relate it back to something you're familiar with, flow in a pipe. So let's just do this. Let's just talk about the area and compare the area of the pipe. What's the equation in terms of diameter? Pi d squared over 4. What would be the area for this non-circular shape, which for this illustration is a rectangle, dimension A and B? Is it A times B? Good. Then you can talk about the average velocity going down. That would be the same. U average. What about the perimeter? What is the perimeter for flow inside of a round pipe? What is that? It's pi d. It's that wetted perimeter, they'll call it sometimes, thinking about water flow. If you take a cross-sectional cut, it's the length of the perimeter that encloses. So let's go over here. What is the perimeter for this? Yeah, 2A plus 2B. And so then you can come up with the definition, other people have worked it out, for the hydraulic diameter. D subscript H. Why D, diameter? Why subscript H? Hydraulic. So it's hydraulic diameter. And what they want is they want the hydraulic diameter, regardless of the formula, to equal the physical diameter for a round pipe. So what is the equation for the hydraulic diameter? It's 4 times that cross-sectional area. Sometimes they put a C on it. Maybe they put AC here or C. Sometimes it's the cross-sectional flow area divided by the wetted perimeter. Sometimes they'll put a W here. Sometimes leave off all the subscripts. It's just 4A over P. So for this case, to see, does it actually give you back the diameter for a round pipe? Well, 4 times the area, pi d squared over 4. And then the perimeter, pi d. And so sure, the 4's go, the pi's go, and you're left with truly the physical diameter. So, all right, so let's come over here now. What is the hydraulic diameter for this rectangular section, cross section A and B? So it'd be 4 times A times B divided by 2 times A plus B. You can simplify it a little bit, 2AB divided by A plus B, but you're pretty well stuck sometimes. That's just what it is. All right. So now you could treat in the calculations something that's not round by something, treat it as if it's round using its hydraulic diameter. I'm going to go ahead and skip this, but basically you'd have a cross section that's 5 centimeters by 8 centimeters, rectangular duct. You calculate the Reynolds number. What's the Reynolds number? Rho, some U average, D over mu, but we don't have a D, so we use a hydraulic diameter. And then you would say whether or not the flow is laminar or turbulent, compare it to 2300, the critical Reynolds number for flow inside of a pipe. Well, we have to get the flow into a pipe, and it can come inside from a large tank. It can come inside with the protrusion from a large tank. It can come inside from a large tank which has a very good bell mouth shape to the inlet. But somehow it's going to get into the pipe. And there's going to be a distance starting from the entrance down before it becomes fully developed. Maybe at this point after it's fully developed. But before, what's happening to the velocity profile? Let's think that it's going to eventually become laminar. And by this case, the velocity profile is that nice quadratic shape. But over here, let's say at this location, what's that velocity profile look like? Very steep, flat in the middle, and steep again. It's as if the fluid in the core hasn't felt the viscous effects from the walls of the pipe coming in. It takes some while to become fully developed. So think about the center line. And you have the growing influence of the presence of the stationary walls with the no-slip boundary condition being felt into the core of the material pipe, and hence you have a developing region, the entrance region. So the velocity boundary layer is growing. I know that I kind of sketched it right there in purple, but it's growing until it gets to the middle of the pipe. It grows from all sides inward. When I do the cross section, I just have the top and the bottom. But for a round pipe, you have right side, left side, top, bottom. It's just growing from the walls toward the center line. So we think maybe the growth of a boundary layer, and it's thicker as you go. Let me try and draw it like this until it gets out to R. And then when it gets to R, close enough to R, it's fully developed. So we have this concept of becoming hydrodynamically fully developed, meaning the velocity profile and the viscous effects are felt throughout the system. As you go, once you are fully developed, as you continue to go down the pipe, the velocity profile is not changing anymore, is it? If I start changing the diameter of the pipe, adding more fluid, removing fluid, well, things do change. But if I don't do any of those, then the velocity profiles, it's some steady state profile, and it's not going to change. Well, what is that length, entrance region length? Let's say the length to become fully developed hydrodynamically. Well, it depends if you're eventually going to be laminar or turbulent flow, meaning that the critical Reynolds number is less than 2300 or the critical Reynolds number is greater than 2300. So what is the equations and how am I going to analytically develop it? Well, we don't analytically develop it. A lot of people have studied this and experimentally found that it's about 1/20th times the Reynolds number times the diameter. Okay, and then if it's going to be eventually fully developed turbulent, what is it? It's around 10 diameters. It's not really a function of Reynolds number. These things probably, if you're going to work in the area of fluid flow and pipes and other things, this is probably one of the things you really want to know. And most flow in pipe is turbulent, and so you need to be 10 diameters down the pipe for it to be fully developed after some sort of disturbance, as like it's being introduced into the pipe. That's a disturbance. Okay. Let me try and ask this question. So, do the flows for laminar, do they take a shorter distance to become fully developed, or do they take a longer distance to become fully developed? Longer? Okay. Do this. It really depends on your Reynolds number, doesn't it? Give me a range of Reynolds numbers for laminar flow. What would be kind of a high-end number for Reynolds number for laminar flow? About 2300. Let's round that off to one significant digit. Give me one significant digit on the maximum. 2000. A lot of books will quote just 2000. So for laminar flow, I mean, this equation doesn't really work for anything greater than 2000, because if it's greater than 2000, isn't it turbulent? But let's take a look at some range of Reynolds number that are lower than 2000. Could you have a flow with 200? Could you have a flow with 20? So it's kind of a pretty broad range of ranges of Reynolds number from a maximum down. Oh, you could have a Reynolds number of 2, you could have a Reynolds number of 0.2, but let's just evaluate 2,220. Let's pick the 20, okay? So if I have a Reynolds number of 20, how many diameters do I need to go before it's fully developed? 1 diameter. Did I do the math right? How about if it's 200? Reynolds number is 200. How many diameters do I have to go before it's fully developed? About 10 diameters. And if it's 2000, what do you think? About 100 diameters. So make the comparison. Is the laminar always quicker to become fully developed than the turbulent? Not really. If it's laminar, high-speed laminar flow, how do you like that? High-speed laminar flow. Well, laminar flow with the Reynolds number in the vicinity of 2000, this would predict that you need about 100 diameters to become fully developed. That's larger than the 10 diameters for the turbulent flow. So there's no easy answer of which one develops quicker. It could be 1D or less, 10 diameters, 100 diameters for laminar flow, where you just compare it to the 10 diameters for the turbulent flow. Now, I did allude to the importance of this result if you ever work in fluid flow, pipe flow out there in engineering, because a lot of times they have short runs of pipe and they have fittings and then they have something else happening to it, but they need to measure the flow. And they need to put a flow meter into the pipe. This is so common. It's unbelievably so common. And when they put a flow meter into the pipe, the flow meter, guess what it assumes is coming into the pipe? fully developed. I mean, the manufacturer of the flow meter is going to test it, and they're going to test it. They're not going to test it on the 1,000, 10,000 different configurations that you could have in the field. They're going to test it on the one configuration, which is a very long pipe before it hits the flow meter, a long straight pipe before it hits the flow meter, indicating that it's going to be fully developed flow before it hits the flow meter. And most of the time it's turbulent, fully developed flow, right? They can't test, and they won't test, and they're not going to test, put a 45-degree elbow, 3 diameters before the flow meter, or put a 90-degree, or put a union or a T right here and bring in a flow and then turn it and then move it here closer, further away. There's too many things to test. They're all based on that you have a nice long straight run before you hit that flow meter, and now it's coming into it with a nice uniformly developed, fully developed velocity profile. Now, do you think that's out there in practice? No. And so if you're a young engineer, a new engineer, you start looking for that, keep that in the back of your mind when you're looking and walking around plants or looking at designs on paper. And say, okay, we have a flow meter right here. We want accurate measurement of this. What's upstream of it? Actually, you also have to worry a little bit about what's downstream of it too, but primarily upstream. And I know that at the university there was a little bit of a discussion a number of years ago because they were buying and selling a quantity based on the flow through a pipe. They found out that had been reading erroneously biased, like about 15% for a number of years. I mean, you would get upset if you worked for some company and found out that they had docked your pay 15% or something. 15% is significant. And they traced it to basically trying to figure out how to recalibrate that flow meter because it didn't have the correct inlet conditions to it, to make some adjustments to compensate the injured party, the person who had been overpaying, and rectify the situation. It happens a lot. Okay? So there you go. So nice number to remember from today's lecture in this class, anything else, 10 diameters. Why? Because a lot of flow in pipes fully developed, it's turbulent flow and it needs to be fully developed before it hits a meter. Well, let's go ahead and do the derivation for the flow in a laminar pipe. What I did was I wrote this out so I could go a little faster. Basically, it's in every fluid mechanics textbook. So you start and you develop a little differential volume of fluid. And you look at the forces on it. It has pressure pushing at X, pushing it in the positive X direction. Pressure at X plus delta X, pushing in the negative X direction. It has a velocity profile that is, think about the velocity here. It's slow and fast. So out here it's slow, and on the inside it's fast. Hence, you're going to have the faster flow trying to motivate through viscous effects on this bottom side of that element in the positive X, and on the R plus delta R surface, it's going to be slower and it's going to have a viscous effect in the negative X. See that? And now, this is a two-dimensional cut, but what does that really look like? It's revolved around that axis, the axis right here. So you have the pressure, the viscous, you combine them for fully developed conditions. There's no acceleration of the fluid through it, through the control volume. It balances equal to 0. You divide the whole equation by delta X, delta R, take the limit as delta X goes to 0 and the limit as delta R goes to 0, you get a nice DE, differential equation. You use Newton's law of viscosity for this viscous effect. And I have it as a function of the velocity U is a function of R. That's my differential equation with two boundary conditions. It's second order space. I'm ready to solve it. Forget that I'm an engineer now. Pretend I'm a mathematician. And just solve that differential equation with two boundary conditions. You just separate, integrate, apply the constants of integration, and you get this velocity profile, which is what we already expected. It's a parabolic. Where's the maximum speed? In the middle. Where does it go to zero? At cap R, the wall. Can I calculate the average? Sure. It's just math, 1 over a du integral u dA. And for that velocity profile, you find that it's 1/2 the maximum. And then you can go back to the expression here for what the maximum was. The maximum can be related to the pressure gradient down the axis of the pipe and the radius, or the pressure gradient, viscosity, and diameter. So just bring that forward, and now you get an expression to say that the pressure gradient with a negative sign in it. Why do we put the negative? Because as I'm going x positive down the pipe in the direction of flow, is the pressure going up or going down? It's going down. So dP dx is negative by nature. It's going from high pressure to low pressure in the direction of increasing x. Hence, we like to put a negative in front of it to talk about a positive pressure gradient. All right. And it's related to the average speed, 32 mu, the viscosity divided by diameter squared. Well, you say, if I knew the length of the pipe, and it's fully developed, and I knew this is the pressure drop or loss per unit length, then I could get the pressure loss for that given length. True? We introduce a dimensionless term known as the friction factor, F. This is 3 strokes on that equal sign. What does that mean? What does 3 equal sign mean? It's a definition. It's defined as negative dP dx times the diameter divided by 1/2 rho u squared. What does the denominator of this friction factor look like? 1/2 rho u max squared. What does that look like? What's it look like? Yeah, pressure. It's our velocity pressure, our dynamic pressure. And then this term right here, you can replace it by if you wanted to, you could put the pressure loss per unit length and replace that dP dx. But okay, you recall from our analysis that the maximum speed, the viscosity, diameter squared is related to negative dP dx. You put into the friction factor definition for laminar flow. This is only for laminar. This is always, that's the definition of the friction factor. But you put in what is dP dx for laminar flow, and you work out a very simple relation. Box it. Remember it. It says that the friction factor for flow, fully developed laminar flow, is equal to 64 over the Reynolds number for fully developed laminar flow in a pipe. What is the Reynolds number? Here's the definition, rho ud over mu. Let me just jump forward then. I'm going to skip some problems. So we have that the friction factor is 64 over the Reynolds number for flow in a round duct or pipe. What happens when I have fully developed in a rectangle or fully developed flow in an ellipse? Well, somebody probably is doing their master's thesis or doctoral dissertation years ago said, I can solve that problem. And they did. And they reported it in the literature, and there you go. Somebody else has worked it out. They solved that problem. So depending on the A to B ratio, that aspect ratio, here is the friction factor. It's some number divided by the Reynolds number, depending on that ratio. How about for the ellipse? Same thing. What is the ratio? And here it is. Notice that the 1 on the ellipse, when A over B is 1, you're back to a pipe. And you're back to 64 over Reynolds number for flow in a pipe. This table is nice to see in the textbook. I think it's in every textbook, but let's be honest. How many times do we have laminar flow in engineering applications with water and air? It's not as common as you might think. Yes, there's a lot of cases where there's laminar flow. But if you go in this building and look at a pipe and say, I wonder if there's laminar flow in that pipe, it's probably not. It's probably turbulent flow. Especially if that pipe's pumping chilled water on one of the hottest days of the year and the system's running at its maximum flow rate. It's that. Same with airflow and ducts. They fight to get as much air into the room, and they want to put it through a very minimum head space between the ceiling and the next floor. They can't put big ducts in there, so they put as big a duct as they can afford to put in there, but they move the flow pretty fast without making a lot of noise. And so it's a trade-off, but anyway, it's turbulent flow. Now, there are a lot of other cases where you do have laminar flow in biological systems and some other engineering systems, but it's not like the world is 50% laminar or more. If you look at the analysis in the fluid mechanics textbooks, you get maybe sometimes I remember I had this perception, it's like, wow, all this stuff devoted to laminar flow. There must be a lot of laminar flow. No, it's just you can analyze it. Turbulent flow is like, well, we can't have such a detailed analysis like we can for laminar flow. Hence, we have to rely on experimental observation. Hence, you only devote a page or two to it compared to the many pages of the derivation of laminar flow. I'm going to skip this. Let's get turbulent flow in pipes. So when you have turbulent flow, how is it described? You can think of it being mixed, disorderly, fluctuating, swirling, chaotic, whatever description you like. But if you introduce a little fluid packet, it doesn't stay in that same lamina or zone as it flows down the pipe. It could be bumped around and end up all over any different parts of the cross section of the pipe as it goes down the pipe. So the velocity profile, we should know, is compared to the laminar profile is going to be more blunt. It's going to be more blunt. And remember, for both of these, maybe I tried to show both of these to have the same average speed, right? For the laminar profile, what was the maximum compared to the average? For laminar, U max compared to U average was what? 2. And then for turbulent, U max compared to U average, is it going to be greater than 2? No, it's not going to be greater than 2. It's going to be less. Maybe I should have written it like this. The average, U average, is maybe 80% or 90% of the maximum. So reciprocate 0.8 or reciprocate 0.9. 1 over 0.9, what is that? 1.11. 1.2, somewhere in there. So let's say 1.2, 1.11, 1.25 times U average. So it's a lot flatter, and it still has to have that no-slip boundary condition. But we don't have a nice packaged analytic expression for it. Well, we can make one that's close, like we did before, and then analyze it, but it's not like the nice analytic quadratic profile for laminar flow. So what we find is that you can do dimensional analysis, and maybe we should do that, to get the friction factor as a function of Reynolds number and relative roughness. We just came out of that chapter, right? You would think of this, you would say, well, I want to calculate the pressure loss in a pipe. What's it a function of? How long is the pipe? What's the diameter of the pipe? What's the average velocity of the flow down the length of the pipe? What's the viscosity? What's the density? And the pipe could have some roughness, wall roughness. And so we set up these parameters like this. Let's go ahead and do it. It's probably a good exercise. What are the primary or fundamental dimensions for each of these terms? What about for the wall roughness? I'm going to put it in SI units, even though it should be length. I'm going to put it in meter. It's easier for me not to work in dimensions, but actually to work in the SI unit for the term. How about for the density? Be kilogram per meter cubed. Professor, I think you should use mass per length cubed. Great. Okay. Viscosity. Do you remember what one that? Kilogram per second meter, per meter second. Let's take a look at it. Does anybody? I'm going to double check. Kilogram per meter second. You're good. A+. Give them a star. How about for the velocity? Meters per second diameter. Meters length. Meters. And then the pressure loss. Well, let's work it out a little bit. So the pressure is a Newton per meter squared. The Newton is a kilogram meter per second squared per meter squared. So you're going to get that it's a kilogram per, whoops, I didn't want to change that color, kilogram per meter second squared. Let me see if you agree. If you agree, give me a thumbs up. Perfect. Very good. Now, how many primary dimensions are there? 3. How many parameters did I introduce and say? 7. So how many fundamental units would I expect? 4. True? Let's count them up. 1, 2, 3, 4, 5, 6, 7. Minus 3, 3, get 4. So I picked the ones that I want to build around. I'm going to build around the pressure. I'm going to build around this one because I know it's going to give me the Reynolds number. And I'm going to build around the relative roughness. Okay. So let's go ahead and do the pressure. If you say that you have the pressure loss and it's a kilogram per meter second squared, I want to get rid of either kilogram or, yeah, it looks like I'm going to get rid of kilogram using rho. So how do we, let's put 1 over rho, kilogram per meter cubed. That work? All right. So we got rid of the kilograms. And looks like I want to get rid of time using velocity next. So we divide by v squared. Would that give meters per second squared like that? Would that get rid of the time squared? Let's see how many meters we have left. It's done, right? So you have P loss divided by rho v squared. That would be one of your pi groups. We've already done the viscosity, so we know that 1 over mu, and then we're going to get the rho, the v, the d. That'll give us the Reynolds number. That'll be dimensionless. And then we're going to get epsilon over d. True? And so I need to pick a 4th parameter, and I need to pick it I'm kind of doing a little backwards here, but this is the way they do it anyway. I need to, which one of these have I not used? Which one have I not used? I haven't used length. So what we can do is you can introduce L as a fourth parameter, because we needed 4 pi groups, and divide by D, and you're done. Okay. So you could get that this parameter PL divided by rho V squared. Put a 1/2 in front, you can, and make it look like our traditional dynamic pressure is a function of, then you can have the Reynolds number, the relative roughness, and the length. That makes sense? Last time you did a quiz, and a lot of people, this is the way you really write or express those results. This is a dimensionless parameter as a function of other dimensionless parameters. Okay, let me ask this. Could I tell what is the relationship between this term and that term? If it's fully developed, as I increase the length, let's say I went L, then I went 2L, then I went another 4L or something, what's happening to the pressure loss? Here's a pressure loss over the L, then I went to 2L. I mean, did it double the pressure loss? If I double the length, do I double the pressure loss? If I triple the length, do I triple the pressure loss? It's fully developed flow in a pipe. Yeah. And so what you can do is it's a function of the Reynolds number and the relative roughness times L over D. Well, why don't I now bring that L over D to the other side, and I'll get P sub L is D over L divided by 1/2 rho V squared. Remember what P, pressure loss over the length of the pipe, is? Negative dP dx. And so what I get is I get negative dP dx times diameter divided by 1/2 rho V squared. That's a function of the Reynolds number and the relative roughness. And so that's what we got right here. The friction factor, what was the friction factor defined as? Negative dP dx times d divided by 1/2 rho V squared. Is a function of Reynolds number and relative roughness. Okay. Well, there's some correlations that go back quite a ways. I didn't put them all, I just showed two of them, where they're trying to fit a lot of experimental data to a simple correlation. So here's a friction factor, and there's the Reynolds number, and there's the relative roughness. Now there's a logarithm in this expression, but it works pretty well. But the only problem is if I really want to get F out of given Reynolds number and given relative roughness, guess what I have to do? It's on both sides of the equation. It's implicit equation, it's not explicit. I'd have to iterate. This equation, Holland equation, if I give it the Reynolds number and relative roughness, I can just calculate the friction factor right away. But these are analytic expressions that fit correlation, that fit the data. Here is probably the most, how do I say it? The most important diagram or illustration in the typical undergrad fluid mechanics textbook. It's called the Moody Diagram. And I like to spend some time on the Moody Diagram. And I don't know if I'll do it this semester, but I have done it before in quite a few classes. And last semester, I think I did it when I did the thermal systems design class. I said, I'm going to tell you one of the questions on the exam right now. The question will be, here's a blank sheet of paper, reproduce from memory with no notes and no anything else, with as much detail and accuracy as possible, the Moody diagram. Blank sheet of paper. You would be amazed. I tell students that'll be on the exam. That'll be your first question. After you turn that in, I'll give you the rest of the exam. You'd be amazed how accurate reproductions I get. They're phenomenal. They're really good. But I think this diagram is so important, and you can answer so many questions out in the field if you're a practicing engineer. If you have this concept in your mind, very quickly answer questions that it's worth doing. So now that I've hyped up the Moody diagram, let's take a look. What's on the x-axis of the Moody diagram? Is it the Reynolds number? Is it in log scale? It is in log. It's not linear. It's log. It covers a range of cases. Here's 1,000 Reynolds number. Sometimes they'll even put it 10 to the 2, 100. Can you tell me what is the type of flow that you have if you have a Reynolds number down like 1,000? It's laminar flow. And then you're going out 10 to the 4, turbulent, 10 to the 5, turbulent, 10 to the 6, 10 to the 7, 10 to the 8. Whole range of turbulent flow. Huge. I mean, it's a wide range. Now, let's take a look at the y-axis. What's plotted there? Friction factor. Linear or log? Linear or log scale? It's kind of a funny scale. Here is 0.01. Where is 0.1? Okay. What is the magnitude between these 2 points right there? Isn't that 0.01 change? 0.01 change? So the distance right here is 0.01. What is the difference between 0.01 and 0.02? What does that change? 0.01 change. So with that information, comparing the length of this line visually and the length of that line visually, is it a log scale or a linear scale? It's a log scale. It's a log scale. Now, does it cover a whole range of numbers or just a much smaller range of numbers than the Reynolds number on the x-axis? Remember, this is factor of 10, factor of 10, factor of 10. It's roughly only one factor of 10, isn't it? But they still put it on a log scale. All right. So right away, if you're ever doing any work and somebody says, I think I calculated the friction factor to be 4.3. What are you going to say to that? You got a friction factor of 4.3? Really? What's the maximum number on the Moody diagram right here? 0.1. You should be skeptical of anything over 0.1. Or you say, are you sure it's not maybe 0.043? Are you off by, 100? Somebody comes in and they say, I calculated the friction factor, it's 4 times 10 to the minus 6. What do you say? I don't think so. I think a pretty low value of the friction factor is about 0.01. So really, this arms you with a lot of information. It's like your friction factor, if it's not in that range, be skeptical. Because this covers a wide range of numbers. Now, the Reynolds number, somebody could have a wide, I have a Reynolds number 10 to the 7 or 10 to the 6 or 10 to the 5. Yep, possible. All right. Now that we got the two axes down, we know that we have the laminar flow region. So what is this curve right here? It's for the fully developed laminar flow. Friction factor is 64 over the Reynolds number. Why is it sloped like that? Well, on a log-log plot, this is a straight line, isn't it? So let's go back and check that out. Let me do this. Friction factor is equal to 64 over the Reynolds number. take the log of both sides, log of friction factor. How do I take the log of something over something? Is it the log of 64 minus the log of the Reynolds number? Yeah. And so you can see now that if this is my y-axis, this is my x-axis, it's negative 1x. So this slope is negative 1, straight line, and that's like an intercept. Okay. If you, oh, let me move on. Now that you have around 2300, somewhere in that vicinity, there's not a clear move from laminar to turbulent. But if you do, it's going to have to transition up and get on one of these curves depending on the relative roughness of the pipe. Right over here, these are the coefficients that tell you what is the value for each of these lines of constant relative roughness. So this is the line of relative roughness of 0.002. Okay? But they come in and they have an effect on the turbulent flow, friction factor. But for the laminar, we just did it for a smooth tube, and so now it transitions, and now you have to figure out where you're going to go to. This is kind of a no man's land. There's not a high level of confidence in the friction factor in this vicinity where it's transitioning between laminar and turbulent flow. What would affect it? Little vibrations in the laboratory or in the machine room or in the building, wherever that pipe is located, that could help it either turn turbulent a little earlier or not. Okay. So now that you're out in the turbulent region, notice that, let's pick one of these curves, this one that's 0.001. It's coming here, then it comes up, and it goes right into there. How about another curve? Well, if you go down, down, down in relative roughness, you get to essentially the smoothest pipe that you get. That's the bottom curve out in this turbulent region on the Moody diagram. Smooth pipe. Are there any engineering applications where pipes are pretty smooth? Actually, quite a few. It really is, quite a few. Drawn copper tubing. There's a lot of water that goes through drawn copper tubing, right? Maybe it's not that big in diameter, but there's a lot that goes through it. Guess what? It's really smooth. Let's take a look. Over here, they give you some roughnesses of materials. Do they show you copper on there or not? Drawn tubing, 0.0025 millimeters. That's pretty small. Okay. What else is really, really small number? Glass, plastic, and what's this? Perspex? Never heard of it. But they have a number of different plastics, okay? But do we have any plastic pipe that carries a lot of water? A lot. A lot of the pipes that are even larger, big plastic pipes. They're really pretty smooth. Do I have many glass pipes? Not really, but there's a lot of plastic pipes out there. So it's amazing that, yes, you have a lot of smooth pipes. You also have a lot of rusty pipes, cast iron, old sewer pipes, concrete. Well, we do carry water in concrete pipes and stuff, but yes, they become very rough. But either the pipe becomes rough because of stuff that builds up inside of it, like rusty pipes, or not. Anybody gotten water out of a house that hasn't had water run through its line very much lately, and then all of a sudden you have to wait for it to get clear? What are you seeing? Rust in the galvanized pipe. You see it a lot in older homes. So that's just a lot of rust. Anybody taking old pipes apart, plumbing and homes, and take a look? Whoa. Or you ever had to fix one that has pinhole leak? or have to go in and use a pipe wrench on one and it just sort of crumbles on you because the wall is so thin now? Yeah, pretty common. That's why the plumbers, when they do repairs on old homes, they're really cautious because the pipes are very fragile in a lot of cases. So anyway, yes, you do have some where you get the whole range of conditions where it's pretty rough to really pretty smooth. But the bottom curve on here is for a smooth pipe. So let's do this. Let's take a look. They have this dashed line, and it separates two regions, region to the right and the region to the left of this dashed line. How do you describe what is the difference in these two regions on the Moody diagram? What's a characteristic that you observe? They introduce this dashed line. It separates something from the right, something from the left. What does it? You can make the observation. What do you see? Well, let me do this. At the end of last chapter, we talked about Reynolds number independence. Remember that? Okay. Here, I'm going to ask you, to the right or to the left, one of these functions has been simplified. In general, we have that the friction factor is equal to a function of the Reynolds number and the relative roughness. Okay? It could go that the friction factor is a function of only the Reynolds number, the friction factor is a function of only the relative roughness, or that the friction factor is truly a function of both Reynolds number and relative roughness. Does that make sense? All right, let's go back and talk about this laminar flow curve. Which one of these is true? A, it's a function of, for this laminar flow curve, it's a function of Reynolds number and relative roughness, or B, a function of only the relative roughness, or C, only a function of the Reynolds number for the laminar flow region. C, that's right. I'm not asking hard questions. But if I don't ask simple questions before I get to a harder question, guess what? The whole class will give me the wrong answer on the harder question. You ready for the harder question? Now I want to talk about this region out here, to the right of that dashed line. They call this sometimes the complete turbulence region. They give it a name. Beyond this is all the complete turbulence, or total turbulence, or some other term. Well, tell me, is the friction factor like A, a function of relative Reynolds number and relative roughness, or like B, a function of relative roughness only, or like C, a function of Reynolds number only? A, B, or C? I'm going to walk around and see what you write on your paper. I hope I asked a clear question. So very good. A lot of you had that right answer, that to the right of this dashed line, in this region out here, which is often called complete turbulence region, I don't like the way where they put this on here, they should put it up there, that the friction factor is a function only of the relative roughness. See, if I was out here, let's say on this line of 0.001 relative roughness, and I was at this Reynolds number, and then I increased the Reynolds number, and I increased the Reynolds number, and I increased the Reynolds number, what would happen to the friction factor? It would remain the same, about 0.02. So it's really only in this region that's between the smooth tube and this dashed line where it truly is a function of both Reynolds number and relative roughness. Sometimes they call this here a transition region, and this one also, it's not completely turbulent, but it's a turbulent region where it's a function of both. All right. Would you like that question on the exam? Professor, if you're going to tell me the question on the exam, I can be prepared. I haven't made up my mind yet, but it could be this semester. I say, here, blank sheet of paper worth 10% of the exam. with as much detail and as accurately as possible, reproduce the Moody diagram. All right, so let's spend a little time on this problem. So if you're given air with a density and viscosity, and it's flowing in a 25 centimeter round duct at 500 liters per second, the roughness is 0.5 millimeter for duct roughness. Can you calculate the Reynolds number? How would you calculate the Reynolds number? Get the rho from there. The velocity, average, maybe I put a V for velocity or U for velocity. I'm going to have to calculate that velocity. V is the volumetric flow rate, Q divided by the area, or Q divided by pi d squared over 4, the cross-sectional area for the round duct. So I can calculate that velocity. We have the diameter here. And then we have the viscosity, mu, here. And when you calculate that, we'll get right at 170,000. Okay. Is it dimensionless, or there's some units on there? Is it something like meters squared per second? It's a Reynolds number. It's dimensionless. Okay. So you can also calculate the relative roughness, which is the roughness divided by the diameter. There's the roughness, there's the diameter. And the relative roughness comes in at 0.002. With the Reynolds number and relative roughness, you can go to the Moody diagram and calculate the friction factor. So let's take a look. 0.002 is this line right here. So somewhere along that line, because it was 170,000 for the Reynolds number, I know it's turbulent. So 170,000 is 1.7 times 10 to the what exponent? 10 to the what? 4? 5? Which is around 2 times 10 to the 5. So let's find 2 times 10 to the 5. There's 10 to the 5. Here's 10 to the 6. Is that 2 times 10 to the 5? Is that 2 times 10 to the 5 right there? So a little bit less, maybe right in here. There you go. There's 1.7 times 10 to the 5. What's the friction factor close to? You tell me. What's the friction factor? 0.02 what? It's between 0.02 and 0.03. You give me the next digit. 0.02 something. 5. Anybody else? 5. So we run over here and we find that's the closest number. 0.025. You have to do a few of these by yourself to really absorb the material. And then what's the velocity pressure? Velocity pressure. What do you think they're asking for? The dynamic pressure. 1/2 rho v squared. True? And so if you calculate it, you'll calculate it at so many 62 Pascal. The velocity pressure. Okay. Let's continue on. So this is the same problem, except there's a typo. 500 liters per minute. And the pressure drop. What's the pressure drop in a run of 25 meters? So we had calculated that the friction factor was 0.025 and the velocity pressure was 62 Pascal. How do I calculate the pressure drop in a run of 25 meters? Well, you go back to the definition of the friction factor. It's that pressure loss or pressure drop, diameter over length divided by 1/2 rho v squared, or pressure loss, diameter over length over the velocity pressure, or the pressure loss is equal to the friction factor, length over diameter. Did I mess that up? This is length over diameter. length over diameter. Friction factor, length over diameter, times the velocity pressure. There you go. So we put in our 0.025. We put in our 62. We have a length of 25 meters. And a diameter given, 25 centimeters. So you calculate it's around 150 Pascal. And then the next question, what's the pressure drop in a run of 25? Isn't that exactly the same question? But look at the answers that they're giving you. What are they giving you? They're giving you pressure drop or pressure loss in, what are those units? Inches of water gauge or water column. Very common when you have airflow, they measure the pressure drop in inches of water column. Well, how do we convert between those two units of pressure? Let me go ahead and pause and see if you can do that, okay? All right, well, thank you for pointing that out. This needs to be fixed. So it was D over L. Don't know why I questioned myself. D over L. There, I knew it was L over D here. Friction factor, L over D, velocity pressure. Okay, so how do you express a pressure loss in some funny units like inches of water column? Well, think about if I have a long manometer and this manometer is filled with water and the rest of it's filled with air. It's connected to my pipe or duct that's flowing. Air is the fluid flowing down here. And I measured the pressure loss between one point and the other point to be 150 Pascal. Well, what should the manometer do if the water is sitting in the bottom of the manometer? Shouldn't it shift a little bit? And if it shifts, is it going to shift this way or is it going to shift that way? The first way, right? And so there's going to be a little difference. It'll be a little higher. And so there's a little H right there. What's that? That's the height of the water column, measuring or indicating the difference in the pressure. So the pressure loss is the delta P, is rho of the water, G times H. So the H is the inches of water column or water gauge is equal to pressure loss divided by rho of the water, G. How many people were going that way? Yeah. Now let's see if our units can work out. We have 150 Pascal, which is a Newton per meter squared. And then we're going to have 1,000 kilograms per meter cubed, 9.81 newtons per kilogram. Newtons go, kilograms go. Meters, I'm left with meters only. And I'll do a conversion that says that 100 centimeters is a meter, and that an inch is 2.54 centimeters. And won't that give me the length or the height of the water column in inches? So if you have a calculator, can you run that for me? A, yeah. I think it's 0.602, right? But the closest number is A. Make sense? Okay. So, is that okay? Ready to press forward? Now, those are major losses for straight runs when it's fully developed. Okay? What about when you have a fitting? Those are called minor losses. Minor is an old term. I wish there was a different term, but it's not. Sometimes you think it's less important losses, but the losses due to fittings and valves can dominate the system. They can be the most significant pressure loss or pressure drop terms in your piping network. But anyway, historically it's called minor losses. So you have a valve here and you start to close it and you compare that to a straight run. And with the straight run, yeah, you're going to have some pressure drop just because of the length of the pipe where the fitting needs to fit in. Often that's negligible. And the pressure loss itself is due to the added resistance because of the valve being present. So major, straight runs, minors, due to fittings. And you have a total head loss. Well, here's the equation for the major head loss. If you want to work in pressure, the pressure loss is the friction factor. How would you get it? Colebrook, Holland, some analytic expression, 64 over Reynolds number if it's laminar flow, or go to the Moody diagram and pick it off. Friction factor, length over diameter, 1/2 rho v squared velocity pressure. Okay. How about for a pressure loss in a fitting? Well, it's proportional to the 1/2 rho v squared in the pipe getting right up to the fitting and through, but they don't have a length to talk about, and so they just put a loss coefficient, typically K, sometimes in a different symbol, but almost always it's K as a loss coefficient. And so this, sometimes they'll put a subscript L on it to emphasize this is the loss coefficient for that fitting. Okay. So if you're interested in the total pressure drop, pressure loss total in the system, well, it's going to be the sum of all of the major, how many straight run sections, and how many fittings, minor pressure losses. Somebody says, you are working in pressure, but I like to work in head. Okay. What was the difference between head and pressure? Pressure is energy per unit volume. Head is energy per unit weight. So pressure typically in PSI, Pascal, head in height, some length. So the equation has the same, this is called now head loss, is the same friction factor, the same length to diameter. It's just not multiplied by the dynamic pressure or velocity pressure, whatever you want to call that term. It's multiplied by the velocity head. So what is going to be this right term right here? 1/2 v squared over g. Isn't that right? Doesn't that work out? Remember 3 forms of Bernoulli's equation? Pressure, energy per unit mass, and head. And now we just are jumping between. So when you see it in a different, you're like, oh, he's written it in terms of head. It looks different. It may look wrong, but it may be correct. Same with the head loss for a fitting. You have a loss coefficient times v squared over 2g. And then you have the total head loss is the sum of the major head losses and the sum of the minor head losses, HLs. That makes sense? Here it's written a little better because it's so important. So I repeat. You have the pressure loss, F L over D multiplied by that term. Velocity pressure, head. For minor, the same, rho v squared over 2, but you have the loss coefficient. These are very common to work in. It's also common to work in head directly. it really only changes what is multiplying F L over D. Okay? This looks like an error right here, doesn't it? Why didn't I write it out like H of L is equal to K sub L times V squared over 2G? I don't know. But it's the right equation. It's just written a little funny. And then I don't know why this is. Maybe I should not have shown this. But here it is, head loss over here. And then here's the sum, the total of the head losses. My major and minor terms. That look good? So now you can talk about equivalent length. A lot of times people will say that I put this fitting into the system. It has a loss coefficient of K sub L. But what I could do is I could say I want to multiply F times some equivalent length divided by diameter times V squared over 2G and have the same head loss. It's just that I'm expressing it now in terms of equivalent length for that pipe with its roughness and its diameter. So the equivalent length for a minor fitting would be the loss coefficient diameter divided by the friction factor. You'll see people talk about equivalent length. Why? Because it's easy to compare. Let's say I have 30 meters of straight run pipe and then I have a fitting which contributes to an equivalent length of 3 meters. Well, then I have a total head loss of 33 and 3 of it's contributed by the minor, the fitting. All right. Well, we move to a modified Bernoulli equation. So let's say I have a pipe and I have flow in that pipe, but it comes down and it does something. It does a 90-degree elbow turn, okay? And then it comes down here. You can do a Bernoulli equation that goes from 1 to 2. Let's write Bernoulli's equation down in terms of units of what? Pressure? So we'd say the pressure at 1 plus 1/2 rho V1 squared plus rho GZ1 plus any pressure gains along that run between 1 and 2 equal to the pressure at 2 plus 1/2 rho V2 squared plus rho GZ2 plus any pressure losses in that section. Well, what now? Forget about the gains. I don't have something adding energy, but I do have some losses. What are the 2 losses that you can see? You would focus. You get better at it. You start focusing. You say, aha, here's a minor loss due to a 90-degree elbow. And here's a straight run and a straight run. So maybe this one's 15 meters, this one's 5 meters, 5 meters. So you have a total of 20 meters of straight run with 1 elbow. And so you would have to go in and say, well, that pressure loss will be the friction factor, the length total for the run, straight runs, divided by diameter times 1/2 rho V squared. And then it also is any loss coefficient for that elbow, 1/2 rho V squared. Let's say somebody put a valve in. There's a valve, and they can turn it. Well, you just add another loss due to that valve. If it's fully open, the loss may be very minimal. If it's partially closed, it could be very important, very, very important. Okay? All right. A valve causes 2.2 meter head loss when the average velocity of the flow is 4 meters per second. What is the loss coefficient for this valve? Okay, well, what are they asking you to solve for? Aren't they asking you to solve for K sub L? And the equation that we know how to get K sub L in is we have H loss, and they give it in units of meters, so I'm going to use that. It's not a pressure, it's a head loss in units of meter, equal to K loss times the appropriate V squared over 2G. True? And so K loss is this head loss divided by V squared over 2G. Just work through the math. You have 2.2 meters of head loss. You have the velocity of 4 meters per second, quantity squared. You divide by, let's put the 2 up here, and the 9.81 meters per second squared. Does that look good for units? And so you can run the number, and you get a K loss of like 2.7. Oh, are there any dimensions on K? No. Were there any dimensions on F? Friction factor? No. Here's another problem. You can work these out. Okay. When you have pipe flow that comes into a pipe, you can have what they call a loss coefficient for the entrance. Okay. Why would you have a loss coefficient for the entrance? Well, try and draw a bunch of streamlines for the fluid. And the fluid that starts kind of out here and just gets into the pipe, it just goes on a nice and easy trajectory. But what about the fluid packet over here, over here, over here? Well, they're not logically going to start and not be in the center of the pipe, but nearer the center and closer to the edge, closer to the edge. And what happens is the fluid packet that comes this way really has to take a sharp turn. And fluid doesn't like sharp bends or kinks. And what will happen is it'll lead to a region of, what's that? It's a recirculation region. It's separated flow. The flow is separated. It gets attached back here, and now it's flowing all downstream. But in that region, there's like little zones of recirculating fluid. It's actually as if there's a contraction in the entrance region. And so you get a energy loss due to the flow. So if you follow a pack of fluid out here, it just has only, let's say, a head, pressure head is the total contribution. But as it moves into this region right here, it's going to be going quite much faster. And so you pick up the combination of the velocity head and lowest pressure or pressure head, but somehow you're going to have some losses. They really could have shown it even coming down here as loss already having occurred due to friction in that. And then, but after you get through the entrance region, you will have some velocity head, some pressure head, and some loss due to friction dissipation, and especially in that with that separation region. So this is like a head diagram as a function of length showing that loss. So you can read more about the vena contracta. It's a point in the fluid stream where the diameter of the stream is the least and the fluid velocity is at a maximum. And Torricelli, we talked about him before, studied this and talked about it. So we have to get flow into a pipe. Hopefully this is something that we can remember for a long time. You can have the pipe that's protruding into a tank. Can you see that inlet is protruding into the tank? Or it can be very sharp-edged, or it can be a bell-mouth inlet or a tapered, smoother inlet. And these loss coefficients can be much different. This is the same tank, the same inlet pipe. The loss coefficient can be close to like 0.8, loss coefficient 0.5, loss coefficient 0.03 as examples if it's really smooth here with a longer radius. So engineers will work to eliminate or reduce these losses because they're really needless losses. to improve the performance of the system. Why is this loss coefficient even larger than this one? Just try and get the most extreme fluid packet, and he's going to have to come around right there, and he's going to have the most severe change, probably a larger recirculation region. It separates, a larger separation zone, and that gives you the larger loss. Here, if you're just helping the flow go around the bend, much better. Used to be, even when I was young, very young, they talk about improving the performance of your engine, automobile engine, right? One of the things you would do is take the head off and port it. Anybody ever heard that term, porting your head? What do they do when they do that? They go in and grind it out to make it as wide of passageways as possible. And they also get rid of any little bumps and protrusions or sharp corners, because any of those sharp corners are just complete losses. And if you're trying to move the maximum flow, get the maximum area, and then help it as much as possible by eliminating kinks and bumps and stuff and corners. So it's a simple principle. You had that principle down before this class, but you see it coming out in this class, in the data, in the tables. What about a loss coefficient associated with throwing the fluid out of the pipe and into the bottom of a tank? So this is a big tank. Here's their tank like here. Here's our pipe. Somebody says, well, you know, there was a difference between a protruding inlet or a blunt inlet or a well smooth rounded inlet like this. I think we should work on the outlet of the pipe just as much as the inlet of the pipe. It makes sense from something, but really, does it really make that much sense? Let's take a look at Bernoulli's from a point here out into the tank, here out into the tank, here out into the tank. So this is point 1, point 2. Think about the velocity at point 1. Is that 0? Is the velocity at 1 0? What about the velocity into the tank out here? There's point 2. Velocity at point 2. Velocity at point 2, the velocity at point 2. In all three cases, regardless of what was the details in this vicinity of the inlet to the tank, guess what the velocity at point 2 is? 0. And so when you do a Bernoulli from here to here, you're going to have, just kind of write it out, you'll have the pressure 1 plus 1/2 rho V1 squared equal to the pressure at 2 plus 1/2 rho V2 squared, 0, plus some head loss here. But the head losses don't depend on, or pressure losses I should write, that don't really depend. You're just going to take that kinetic energy and sort of waste it when you come out of the pipe. And so the loss coefficient in all of these is equal to, if I could do this, cancel, pressure loss is just 1 times 1/2 rho V squared. It's just all of your kinetic energy is just lost to the inlet. That's all. So the loss coefficient, 1, loss coefficient 1, loss coefficient 1. The outlet into a tank doesn't matter. It's the inlet to the tank that matters. All right. If you have sudden expansions, you could have more significant recirculation region, and you get K. Look at the plots in the textbook. Similarly, if you have a sudden contraction, look at the plots in the textbook. If you have gradual expansions, better. If it's sharp, it's worse. So if you have a gradual increase, the K can be reduced. If you have an elbow, the K on an elbow is around 0.30 for a 90-degree standard radius elbow. If you have a long radius elbow, it can be smaller. You're just trying to help it move and curve. If I have a duct, a lot of homes have rectangular ducts in the attic that carry the air. They're made out of duct board. They're easy to install. They need to turn at the corner. A lot of times when they install them, they turn a corner, and it's what I would call a hard corner. If you own an older home, you might want to look up there. You either have flex duct, round, or you have duct board. And the duct board like this is be rectangular. Anyway, looking down, it's really hard for it to navigate that turn. You'll have a large separation region that'll have a large loss coefficient. Maybe the loss coefficient without any help is maybe something like 1.1. Here, a loss coefficient, if you put in some turning vanes, they're little metal inserts. You can buy them if you're in the HVAC industry and you want to help the high performance duct systems. You can buy those little inserts and put them in there. They'll always help. Every time the air is being pushed by the fan, it'll help navigate that turn. It'll drop that loss coefficient to 0.2. That's a pretty good reduction. But most of the homes, they don't have them. Most homeowners, another thing, they don't know. And once it's sealed up, taped up, and in the attic, and it's hot in the attic, you're not going up there. Most of the homeowners don't even know what carries the air in the attic. But it would make a significant improvement. And if you're a design engineer, maybe you're working on a building, and it's, maybe you specify that the contractor that's building it put those in to help reduce the pressure drop on ducts flows. I had a house, I had one of these, I went up in the attic, I looked, it's like, why is that room over here not getting the airflow? The size of the duct was big enough, it's just that 90-degree kink added so much equivalent length to the ducts that it was choking the flow, and it wasn't getting the flow in that region. So, well, I'm going to go ahead and stop for today, and we'll pick up there next time.